All right, so week 2 lecture. Continuing on with chapter 2, a little bit of chapter 9 when we talk about filters. So the first thing we're going to deal with is alternating current. Why is this important? Mainly because that's the easiest way to generate power. You have big power plants that turn turbines, and that creates change in the magnetic field, which creates this alternating current. So generally, your voltage or current source has a sinusoidal waveform, such as the one shown down here. So my voltage as a function of time is some peak voltage, dP, and then the sinusoidal variation, 2 pi times the frequency, generally in hertz, times the time in seconds, and then your phase shift, if you have one. A similar equation for current, so you have some current as a function of time, which is some peak current, then you get some sinusoidal variation. It's pretty much the same. If we combine more than one sine wave, we can make more complex waveforms. So a bunch of different sine waves, get some more complex waveforms. You also get triangular waves. So we'll see some of those in some labs, as well as square waves. We'll see a lot of those in lab this week. We'll see some of them. Very easy way to get a square wave out of a digital signal, it's just being on or off. So if you kind of ignore this bottom part, pretend that this just cuts off at 0. Those are the ones you'll be seeing in lab today. Not today, but this week. So you'll have some voltage kind of on and off, and a square wave pattern coming out of the Arduino to give you that square wave form. But you have those in general as well. So since we're dealing with sinusoidal, primarily waveforms, you talk about things like cycles. So one complete cycle, one complete rotation, essentially, of your sine wave. And then in terms of these phase shifts, so this guy here, B has been shifted 90 degrees away from A. And this one, B has been shifted 45 degrees away from A. This one, we have a complete 180 degree phase shift between A and B. So B, in this case, lags A by 90 degrees. So this 90 degree phase shift, a quarter of a cycle. B lags A because B happens after A. Think of this as the time axis. This happens first. So that's why B lags A, even though it looks like it's ahead of it in terms of spatial. Because this is my time axis, this actually happens first. So that's why anything in front actually lags. So B lags A in both cases. If I look at the alternating current, so I provide this sinusoidal voltage source and look at what happens to my current in a nice simple circuit. So just a resistor, that's all I have in my circuit. So again, my voltage source, sinusoidal voltage source. You can get the current from Ohm's law. So Ohm's law says that the current is just voltage divided by resistance. So it's basically dividing by my constant R, gives me my current. So essentially this Vp over R becomes my peak current, and again have the sinusoidal variation, same sinusoidal variation as the voltage. And so if I have my voltage here, current is generally going to be smaller because resistances are usually more than 1. So my current smaller, but in phase, so 0 phase shift, current and voltage, exact same things happening, just different amplitude. To look at the power is 3 ways you can do it, either current times voltage, or voltage squared over resistance, or current squared times resistance. All 3 give you the same equation in this case, Vp squared over R, essentially my peak voltage times my peak current times sine squared. So that gives me this power curve, sine squared essentially. Now in terms of AC sources, generally when we deal with DC sources, everything's kind of nice because everything's a constant. I have a constant voltage, gives me a constant current. Everything's just one number. Problem with alternating current is I don't have just one number, things are changing, generally changing sinusoidally. And so I kind of want to be able to quantify the amount of voltage or current that I have. The circuit with 1 volt in it is much different than the circuit with 120 volts. So I want to kind of have that differentiated. And so first thing you want to do, or the first thing you think of possibly doing, is just taking the average voltage. Problem with that is the average voltage is going to be 0 no matter what, because you have alternating parts of positive voltage and negative voltage. So no matter what, they all average out to 0. So it doesn't actually help. So the way to avoid that is to take the square and then take the square root. So that's the good old root mean square value. So by squaring things, I make everything positive. Then I take the average. Then I take the square root of that. And that is what these RMS values measure. That way, there's a big difference between 120 volts and 1 volt. So anytime you're given an AC current or voltage, that's generally going to be the RMS voltage unless someone tells you otherwise. So if you're just given 120 volts, you can assume that's RMS. Now, obviously, because this is the average, the peak value is actually going to be higher. So basic way to find the RMS values, again, is you want to square it, then take the average, then take the square root. So that's essentially what this is doing. I'm integrating over the squared voltage, so I'm squaring the voltage. Taking the average is what the integral is doing. So taking the integral from 0 to t, t being the period, so 1 over 1 complete cycle, and then averaging that over the entire cycle, so 1 over t gets that into the average, and then take the square root. That's my RMS value. Same thing for the current. So again, square the current, take the average, take the square root. For the sinusoidal waveforms we saw before, the voltage was some amplitude, Vp, times sine. So Vp, just a constant. You can square it, take the square root, it comes out. Then the average over 1 complete cycle of sine squared is 1/2. And so the square root of 1/2 gives me square root of 2. So for sinusoidal waveforms, the things we deal with the most, the RMS value is the peak value divided by the square root of 2. That's no matter what I'm dealing with, voltage or current, because they're both sinusoidal. So 120 volt RMS actually has a peak voltage of 170 volts. So the peak voltage coming out of your household electrical sockets is 170 volts. Root mean square of that value is 120. In terms of the power, that is the current times the voltage. And so both square roots of 2 multiplied together gives me the peak power divided by 2. And one thing to note, generally DMMs either measure peak voltage or RMS voltage. Some of the cheaper ones go for the peak value. More expensive ones generally measure the RMS ones. It's good to know which one you're actually measuring. I don't think we actually have to measure any alternating current voltage in the labs. You might have to, may not have to. But again, good to know which one you're actually measuring, which one the DMM you bought is actually doing. So next up is capacitors. So capacitor is a device that stores charge essentially. Symbol is basically 2 parallel lines perpendicular to the wires. That's the standard symbol for a capacitor. There's also a special capacitor that's polarized called electrolytic capacitors. In this case, you have one kind of bent line indicating which one's a positive and negative side, because those ones, it's very important to hook them up the correct manner. The positive side of the battery. Otherwise, bad things happen. These standard capacitors with this 2 parallel lines, doesn't matter which way they go can go forwards or backwards. Kind of like resistors, doesn't matter what side they get put on. The kind of standard capacitor we see are the parallel plate capacitors. So you have one plate on one side with some positive charge. So that's basically the positive side of the battery. You have one plate on the other side with negative charge. That's basically going to the negative side of the battery. Same area, some distance between them. Some of the capacitors we use in lab kind of look like these parallel plate capacitors, but rolled up into a cylinder. So that's what a lot of the ones you'll be using look like. Between the 2 plates, you could have a vacuum or just air. or some sort of liquid or solid dielectric material, so something that does not conduct electricity essentially. So an insulator, so some oil, some mica, ceramic, glass, something of that nature. So again, in the ones that you use in lab, the cylindrical ones, there's something between them, then you roll it up into a nice little roll. Capacitance. The capacitor measures essentially how much charge it can hold, so how much charge it can have on each plate. And that's related to the voltage that's being supplied. So the more voltage means there's more charges coming in. So the capacitance kind of is a measure of how much charge is there compared to what the voltage is. Capacitance measured in farads, which are equivalent to coulombs per volt. And 1 farad is actually a really huge amount. If you have a 1 farad capacitor, that is huge. We generally deal with microfarad capacitors in lab that you'll be seeing. So again, relationship between charge and voltage. Capacitance is my constant of proportionality, a lot like resistance is the constant of proportionality between voltage and current, but this goes from voltage and charge as opposed to voltage and current. So the value of your capacitor, the capacitance, depends on the geometry of the plate, so essentially the area and the distance between them, as well as the properties of the dielectric material, so what's between the two plates, and that's where this K and epsilon 0 come in. So epsilon 0, permittivity of a vacuum, K being the dielectric constant of whatever that object is. So here's some values for some standard materials, air, oils, other things. As I said, capacitors, bad things can happen. So as I mentioned before, the electrolytic capacitors, the ones that are polarized, those ones depend on which way you put it in. So they can only go in one way. They can go either way, but you should only put them in one way. If you put them in backwards, they're not going to work. In fact, they're going to blow up. And I do mean that literally. I've been in rooms where capacitors have been blown up by students. I've never done it myself, but I've been in the room when students have done it. So be very careful with those. They're a lot like the LEDs, where one lead is going to be longer than the other one. And just like the LEDs, the longer one you want to put on the positive side to make sure that it's in properly. Again, if you put it in backwards, it's not going to do what you want it to do, and it may blow up. So those are not very good for AC circuits, because AC circuits, the voltage goes back and forth, so the current also goes back and forth. So the current's going to be going both ways. So you generally don't want to use the electrolytic capacitors for AC circuits. Another bad thing that can happen with capacitors is called dielectric breakdown. So if you have too high of a voltage, it exceeds the capability of the dielectric to hold it back. So essentially, the dielectric almost starts to melt. And again, bad things happen. So those are just 2 warning signs with capacitors. Now, putting a capacitor in a circuit, start out with a capacitor just by itself. So just voltage source, capacitor, assuming a sinusoidal AC power source as usual. And so remember, capacitors are related to the voltage and the charge. I want to know what happens to the current generally in circuits. And so current is related to charge because current is the derivative of charge with respect to time. And so if I take that derivative, C being a constant, I just get the derivative of voltage with respect to time. And I know that my voltage source is a sinusoidal voltage source. So some peak voltage times the sine of omega t. That gives me the current as a derivative of that times C. So C times Vp times omega. Essentially my peak current will be those combination of those 3 things times the cosine, because cosine is the derivative of sine. So because of that, cosine is out of phase with sine by 90 degrees. So cosine leads sine by 90 degrees. So the current is going to lead the voltage. So in terms of my current, again, amplitude is generally going to be something smaller than the voltage, but it hits its peak 90 degrees before the voltage hits its peak. And in terms of the power, again, voltage times current, change in energy over change in time. I can get the energy by integrating that power over time, and that gives me 1/2 CV squared. And so again, I have my power curve being the current and voltage multiplied together, gives me that curve there. So again, changes in time. So one thing to remember about capacitors is that they stay charged after the circuit's turned off. So if you have a direct current going in, you're pushing this thing through voltage, the capacitor is going to charge up to that same voltage. If you then disconnect one lead of the capacitor, there's still going to be some voltage in there. So the question, was the other lead allowed to discharge? The answer to that is no. Now you want to think of why. So essentially just pulling one of the leads out of your circuit board. If you pull one lead out, there's nowhere for that current to go, except if you're touching it. If you're holding it, the current then has an option to go through your body into the ground, and so it can discharge that way. So if you have a pretty high voltage source, 20, 30 volts in there, and you disconnect the capacitor by pulling on the lead, you are going to feel it. Again, luckily, we're not going to have to do any of that in our class. The biggest voltage you get out of your Arduino is about 5 volts, and that's not going to hurt. But don't do it with any higher voltage. Don't do it with 5 volts either. So that's capacitors in circuits by themselves. Next up, we have RC circuits. So essentially a resistor and a capacitor in series with each other. So the simplest one is a single resistor with a single capacitor. Generally, I also have a switch in here, generally just because you want the circuit kind of turning on and off. And then you have some sort of output voltage. This is equivalent to the capacitor voltage because they're in parallel. So again, just like we did before, capacitor, we have some current, which is the charge over time, and that's capacitance times the derivative of voltage with respect to time, and this is specifically the capacitor voltage. Just like two resistors, the resistor is going to take up some of this battery voltage, the capacitor is going to take up some of that battery voltage. Kirchhoff's law, those two voltages have to add up to the battery voltage. So I have some voltage VC in my capacitor, some voltage VR in my resistor. And so I can find the current through that resistor by taking that voltage VR and dividing it by the resistance. But again, as I said, that voltage VR have to add up with VC to VB. So VR is VB minus VC. So there's my current through my resistor. So in terms of Kirchhoff's voltage law around my circuit, I have my voltage to my capacitor, voltage to my resistor equals voltage in the battery. We're going to solve this equation for a given set of initial conditions. Essentially, two most common initial conditions are the switch is off, and then at time equals 0, you turn that switch on. So that's going to correspond to the capacitor charging. The other common situation is the switch is on. It's been on for a really long time. So the capacitor is charged. Then at time equals 0, you unhook the switch, in which case the capacitor discharges into whatever's over on this side of the circuit. So we'll see those in a minute. And we have this combination R times C that shows up a lot. So we have a special name for that. Call it tau, R times C. It's called the RC time constant. So units of ohms times farads actually gives you seconds. So tau is measured in seconds. That's why it's a time constant. And essentially a measure of how fast the capacitor charges or discharges. The smaller the number, the faster it discharges. So those solutions I was talking about, so charging, essentially this switch is open, and then at time equals 0, you close the switch. Capacitor starts to charge because the battery starts to give it some charge, some current. The charge on the capacitor, the voltage to the capacitor, is given by this equation, VB 1 minus e to the negative t over tau. So as time goes on, time equals 0. It has 0 volts through it, 0 charge on it. Then as time goes up to infinity, essentially, eventually ends up having the same voltage as the battery. And then discharging the opposite, it's been on for a really long time. It's up to the battery voltage. Then at time equals 0, the switch is opened up. As soon as the switch is opened up, this whole side of the circuit pretty much goes away because nothing can get through that switch. So we're only looking at this side of the circuit. So my capacitor is essentially acting like a battery on whatever this source is. But as it acts like a battery, as it discharges, it has less and less voltage on it. And so the voltage decays exponentially. So in both cases, it either charges exponentially or discharges exponentially. You're going to have really large current at the beginning, and then that current goes to 0 as time goes on. And you can't have a steady DC current, because as you add current, you're adding charge. Keep doing that, eventually the capacitor is going to essentially blow up. So can't have a DC current through a capacitor. Bad things will happen. This cycle of charging and discharging can be repeated. So if you use this sort of switch, so the way this switch is in now, the battery is connected to the capacitor, so the capacitor is going to charge, and then flip the switch to the other side, and that's going to make the circuit just go through the resistor. So my capacitor is going to discharge through the resistor and possibly whatever's over here. And so you keep flipping that back and forth. I'll keep charging and discharging. Of course, you don't want to sit there with your finger switching this back and forth. An easier way to do it is kind of alter this battery. So that's not just one voltage, but it alternates between some voltage and 0. And again, that's really easy to do with your Arduino with the digital pin, just on and off. So digital pin on, digital pin off, on, off. And then that'll make your capacitor charge and discharge. And as it does that, again, you're going to follow these exponential curves. And that's, again, part of your lab this week is to do something of that nature. So there's a difference between a real capacitor and an ideal capacitor. So we kind of assume everything's an ideal capacitor. For an ideal capacitor, so going back to the very first circuit with just a capacitor and just a battery, there's no resistance. If there's no resistance, that voltage would jump straight up when the switch is closed. The capacitor would pretty much instantaneously charge all the way to the battery voltage. Basically, your RC times constant would be 0 because the resistance is 0. And so it would take 0 seconds for that to completely charge. So instantaneously, essentially. In terms of the current would be infinite for those 0 seconds until it's fully charged, which again takes 0 seconds. Real capacitor has some resistance associated with it just by nature. And so you can kind of think of every capacitor as having a capacitance and a resistance. So this is separate from the other resistor that's already in the circuit. And so what that does is instead of charging instantaneously, it has this exponential curve. This resistance is fairly small. So if you just have a capacitor in your circuit, your RC time constant will be fairly small. So this will be a fairly quick charging, but it won't be instantaneous. Similarly here, you'll have a really high current, and then it's going to decay exponentially in my real capacitor. Same thing for discharging. Discharging, if I have some voltage, ideal capacitor drops straight down to 0, but in real life it decays exponentially. And same thing for the opposite side. If you want to get into the really nitty-gritty of what a capacitor actually looks like, it actually has its capacitance, some leakage resistance, some dielectric. So your dielectric is going to have some capacitance and resistance associated with them as well. Then you have your equivalent series resistance and also some inductance as well. But won't worry too much about those crazy ones. But ideally, or more accurately, that's what your capacitor looks like. For us, just calling it a capacitor, an ideal capacitor, is probably fine because most of our circuits are going to have a resistance anyway, and the resistance we hook up to it is generally bigger than its internal resistance. So we might hook up 1 kilo ohm, 10 kilo ohms. The internal resistance of my capacitor might be like 1 ohm. So in series together, that's not going to make a big difference. So now we want to know what happens to my RC circuit responding to a sinusoidal source. So we saw charging, we saw discharging. That's kind of constant voltage in each case. I'm either charging with a constant voltage battery, or I'm discharging with no battery. But if I have a sinusoidal source on there, what happens? And so, same governing equation. So Kirchhoff's voltage law still gives us this equation. RC is still my time constant. Omega 2 pi times the frequency in hertz. Call my source voltage VG as opposed to VB. So it's not a battery, it's not some sort of power source. In this case, my alternating sinusoidal source. So it's kind of different notation there just to denote that. But other than that, same equation. But I do know now, so VB is no longer constant. I now have VG, which is a sinusoidal source, some peak voltage times sine of omega t. So plugging that in and solving this equation for VC, you get that VC is that peak voltage coming out of the power source divided by the square root of 1 plus omega tau squared times, again, the sinusoidal variation. On the sinusoidal variation, there's a phase shift. That phase shift is negative inverse tangent of omega t. So essentially what happens, I have my power source. Power source goes from peak voltage to negative peak voltage. Then the voltage through the capacitor, the voltage will be lowered by a certain amount. That certain amount is this factor on the bottom, 1 plus omega tau squared, square root of that. So my voltage in my capacitors slightly lower, or maybe a lot lower, depending on circumstances, from the voltage being provided by the power source. Then there's also this phase shift. Again, depending on the frequency and the value of the time constant, or the value of the resistance and the capacitance. So voltage across the capacitor is out of phase. And again, the amount by which it's out of phase is going to depend on the frequency, as well as the resistance and capacitance. But those are basically constants. Frequency is generally something you can change slightly easier. So if we look at this, we can define what's called the characteristic frequency, F star. F star is 1 over the time constant, or 1 over 2 pi RC. And then we can look at the amplitude of the previous, or the comparison of the amplitude of the two voltages. So VC divided by VP. So just the amplitudes, and that's essentially this omega t squared becomes F over F star squared. And then same thing for the phase shift, omega t becomes F over F star. Now if you look at that, and in terms of the frequencies, if my frequency is much less than this characteristic frequency, so F over F star is really small, essentially this goes away. I have 1 over 1, so VC is about the same as VP in terms of amplitude. This F over F star is really small, so inverse tangent of 0 is essentially 0. So 0 phase shift as well. So essentially, the voltage of the capacitor is the same as the voltage that's coming out of the power source. That's if my frequency is very small compared to this characteristic frequency. On the other hand, if the frequency is very large, my amplitude goes down by a factor of 2 pi f times tau, so 2 pi times the frequency. Essentially, my voltage to the capacitor gets reduced by a factor of the frequency, whatever it is. So as the frequency increases, my amplitude decreases. And then I get a cosine omega t instead of sine. I'll let you figure out why that is. If you want to ask me in office hours, feel free to do so. So again, pictures of those two functions. So here's my plot of Vc over Vp for very small frequencies, equals 1 essentially, so same amplitude. And as I get close to this f star, the characteristic frequency, it starts to drop, and then it drops linearly essentially with frequency. The same thing for the phase shift. So phase shift starts out at 0. Then as I get close to this f star line, it starts to go close to 45. Then it's at 45 degrees at the characteristic frequency right in the middle, and then starts to go down to negative 90 essentially. If f is exactly equal to f star, the amplitude is reduced by a factor of square root of 2. And as I mentioned, the phase shift is right at 45 degrees. So this type of circuit is called a low-pass filter. Essentially, it's filtering out any sort of high frequencies, because as you see the high frequency, the amplitudes all essentially get reduced down to 0. And so for really small amplitudes, they don't show up anymore. All that's left is the higher amplitude, lower frequency signals. So if you have a bunch of different frequencies coming in, only the low frequency ones will survive. Low being with respect to f star. A good way to measure this change in amplitude is with decibels. So they measure the power using a logarithmic scale. Nice thing about logarithmic scales is if you have a bunch of them back to back, you just add them together to get the total gain or damping. So power is either going to be increased or decreased, either gained or damped by a series of components. You want to know the gain in decibels. So generally decibels is a logarithmic scale, as I said, log base 10. Decibels, you multiply by 10. And so in this case, it's power. So power divided by my input power. So whatever's coming out divided by whatever's going in. Log base 10 of that, multiplied by 10, gives you the answer in decibels. If I have a constant impedance, get what impedance is in a minute. It's basically kind of like an AC version of resistance. Power is proportional to the voltage squared. And so if we're at the scenario where F equals F star, the characteristic frequency, the power through my capacitor divided by the power coming out of my voltage source is the voltage divided by voltage in the capacitor divided by the voltage in the power source squared. And because that has a factor of 1 over square root of 2, when I square it, I just get a half. So at F equals F star, I'm at half power essentially. In terms of decibels, half power, 0.5, is approximately -3. So the -3 decibel point you see a lot, because that's where half power is. And that should be important when we get to op amps in a few weeks. So low-pass filters, we were talking about the voltage across the capacitor. Now I want to look at voltage across the resistor. So essentially, I just changed my circuit. I moved the capacitor up there, the resistor down there, so basically swapped them. So now I'm looking at the voltage coming out being the voltage across the resistor. In this case, I have a very similar formula. For VR, VG, again, have my sinusoidal source. I can solve this to get VR over VP is omega t over, again, the square root, same thing we had before, again, sinusoidal. And then now I have this phase shift, which is slightly different. Instead of negative tangent of omega t, it's positive inverse tangent of 1 over omega t. If we see what happens this time, very low frequencies, they get reduced in amplitude by the same amount. Very high frequencies, essentially nothing happens. So again, essentially very high frequencies, voltage across my resistor, essentially the same as the voltage coming out of my source. So no phase shift, no change in amplitude, or very little change in amplitude, very little phase shift. So this is called a high-pass filter because it lets high frequencies through. It filters out any low frequencies. So in terms of amplitudes, all low frequencies are fairly low, so they pretty much go away. As the higher frequency, generally nothing happens to amplitude. And then phase shift 90 degrees for very low amplitudes, 45 right in the middle, and then 0 phase shift for very high amplitudes. If you want to combine a high-pass filter and a low-pass filter, you now have something called a band-pass filter. So essentially you have two different bands, some lower end frequency, some higher end frequency, and it's only going to let through frequencies in that band. And so basically just connecting two of those Bode plots for the amplitude or attenuation. So you have some high-pass filter, filtering out all the low frequencies, some low-pass filter, filtering out all the high frequencies. Then you have some band pass, which in this case is between 10 hertz and 10,000 hertz, and that's essentially the only frequencies that survive to any appreciable extent. I didn't actually show you how to draw or what the circuit looks like because that's part of your homework, so I'm not going to give you the answer now. You'll have to figure that out later. And then last thing for today is impedance. So the amount of current, change of charge through a capacitor is influenced by the voltage, the capacitance, and the frequency as we've seen. If you have an AC source through a capacitor, the voltage divided by the current, that's what is resistance by Ohm's law. Here we have a voltage through the capacitor. So that's Vp times cosine. So again, my original voltage source was a sine wave, but through the capacitor, it gets shifted by 90 degrees to a cosine. And then my current is the capacitance times change in voltage over change in time. And so what we get by that is negative 1 over omega c, cosine over sine. And so cosine over sine, function of time, so that averages out essentially to 1 in a sense. And so what I'm left with in terms of sort of magnitude of resistance is this factor of negative 1 over omega c. So 1 over omega c, similar to resistance by Ohm's law, units of ohms. And so that is my impedance, kind of like resistance to current flow for capacitors in AC circuits. So this impedance is given a special name called the capacitive reactance. So XC is my capacitive reactance. It's 1 over omega c, or 1 over 2 pi frequency in hertz times the capacitance. Again, this is kind of like resistance, but the difference is that no energy is dissipated. So if I put a current and a voltage through a resistor, it heats up, it takes away that energy. In the capacitor, it doesn't necessarily take away that energy, but it does act as kind of like a resistance for the current, so it will lower the current by a certain amount. High values of capacitance, my capacitor acts like an open circuit, so infinite resistance to current flow essentially, low capacitive reactance, capacitor acts like a short circuit, so essentially no resistance. So both capacitive reactance and resistance are both forms of impedance. When we talk about AC circuits, instead of talking about resistance, we generally talk about impedance, and that acts a lot like resistance does in DC circuits. So the total impedance for an RC circuit, impedance generally called Z. For an RC series circuit, just like series resistors, just add the resistance together. So in this case, my total impedance is my two impedances, the capacitive reactance and the resistance, added together. You can also have contributions from inductors, but we haven't talked about those yet. So that is the theory part of today's lecture. I'll see you later this week for some examples of those topics.